Hello students, hope you are doing good today. So today I thought to bring to you a problem from class 11 in physics, which is vertical circular motion. We have discussed the circular motion in the horizontal plane in great detail in one of the videos. You can go and directly watch it on our channel. But today what we are going to discuss is on the vertical motion, vertical circular motion. So let's say a string is there and you have tied that string to a stone and then you are trying to rotate it in a vertical plane. So yeah, we'll start the video now. But before that, welcome to EdFalco Academy and an epitome of thorough education, which means faster, accurate, affordable, and result-oriented education. Mm, and if you have any doubts, any queries, you can always reach back to us. You can visit our website. We are available on all the channels. You can contact us through any medium that you like. Okay, so let's start this video without much ado. So great. So let's start with this chapter on vertical circular motion. Um, Now, few things to understand while we start this chapter is that in this particular kind of circular motion, the body is actually going in a circular path in a vertical plane. Now, when it is going in a vertical plane, you can think of that gravity will come into play because it's the gravity, the entire gravity field is pointing in the vertical direction, right? The gravitational acceleration exists in the vertical direction. So therefore, we cannot neglect gravity now. Okay. Earlier, we were just talking about a very simplified case of circular motion where we were just thinking like let the body be moving in a circular path and be it any plane, whether it's horizontal or vertical, but there are no other external forces or any other external fields which are applying any sort of forces on this particular on the body which is moving in the circular path, right? That was our, I mean, assumptions, and based on that, we were just seeing that the body was just going in a circular path. Obviously, the velocity was tangential to the to the path, and then there was centripetal acceleration whose value was mv square by r, where r was the radius of the circle, and all these things we have understood, right? And with that assumption, we made a simplified model of what we called as the circular motion. But now here there is the external force which is coming into play when we are talking about vertical circular motion, because the body is moving in a circular path. It is tied to a string, and obviously the string is going to provide a tension force first of all, because it is tied to that. So the string will become taut, or it will become tight as you try to rotate it, so that will provide a tension force, and then there is a gravitational force also acting, right, in the vertically downward direction. So if we now try to analyze this motion, there will come some more factors, but the basic logic remains the same. So, but we'll try to understand each and everything in a detail. So let's say that the body is going in a circular path in a vertical plane like this, and imagine that this is the center, and the body is attached to a string. Let's say it is attached to a string, and there is a mass of, let's say, mass small m. And so now after we have decided all this, what are the forces that will be acting on this body? So one is definitely going to be the tension force, which will point in this direction, tension, right? Which is trying to keep the string taut, and this is the force which is acting on the mass, right? We are talking about mass, so mass is getting pulled inside because of this tension, right? So the forces that I'm going to draw are on the body. Okay, so on this body, the tension is going to be acting in the inward direction. The second force which is acting is the mg force. Now this is because you are moving in a horizontal plane, the gravitational field exists all around, right? In the downward direction. G exists in the downward direction. So therefore, mg force is going to be applied over here. Now let's try to analyze these forces. So let's assume that at any point in time, right, the body is at an angle of theta from the vertical. Okay, so obviously this angle is also theta then, right? And therefore, what are the components of this mg? we can find out the components of this mg. So mg will be, one component will be in this direction, which is mg cos theta. So obviously you need to know the vector components, breaking, and of course the entire vector chapter you should be very clear with, when, because all those are going to help you in this chapter while I'm breaking it. So here I'm not going to explain like why it will be mg cos theta in this direction, but when we are studying the vector chapter, there all these things must be clear. And in this direction, tangential to it, it will be mg sin theta. So some of you might be already aware. Now let's concentrate on these two forces, T mg cos theta. That is the force which is acting in the radial direction, right? In the radial line. So, so they should be responsible for providing the centripetal force, right? And what is the net force which is now acting in the radial direction? You can say it is T minus mg cos theta. That is the net force which is acting in the inward direction. And now this force is what is keeping it in the circular motion. So this force is responsible for providing it the centripetal acceleration. Because you already know that if there is a centripetal acceleration provided, if the body is always being accelerated towards the center, then it will try to keep in the circular path. So this particular resultant force, which is T minus mg cos theta, is going to provide the centripetal acceleration. So, and from our previous basic understandings, we already know that this is nothing but equal to mv square by r, because this is a, it is equal to m mass into acceleration, and then acceleration for a circular motion is v square by r. If suppose v is the velocity at this point, then it will be v square by r. R is the radius of this circle, or if r is the radius of this circle, or you can think of it like the length of this string. So this will be one of the equations, right? This will be one of the equations. T minus mg cos theta is equal to mv square by r. The another important equation will be that you can see that the velocity is pointed in this direction, right? Tangential direction. This is the direction of your velocity. Now you see that there is a retarding force which has come, retarding force in the opposite direction to the velocity, which is equal to mg sine theta. So that means that the velocity is going to be retarded, right? The velocity is going to be retarded. So direction, of course, we knew already that the direction of the velocity was going to change. That we were knowing from our basic understanding of circular motion also. But what we were taught there was that the velocity magnitude was a constant. The value of the velocity is a constant value. The magnitude is a constant value, right? And it was simply given as r omega, right? The value of velocity. But here, what do we see is that it's not constant. Its magnitude is going to decrease because there is a retarding force equal to mg sine theta, which is acting against the velocity, right? And you know that if you are putting obviously that means that it will produce a retardation or deceleration of how much g sine theta. So if you already know that if the velocity is there and there is a deceleration of g sine theta, the body is going to slow down, right? So everywhere as it moves up in the circle, as it's going to move up in the circle, you will see that the body is going to retard, or its magnitude is also going to change, right? Okay, so as it's moving up, the velocity magnitude is also changing. So another important thing is velocity is neither constant in magnitude, neither in magnitude now, and already we knew that nor it was consistent, nor it was constant as in direction, nor in the direction. So in this vertical, so and this is one of the major difference from whatever we are discussing as a vertical circular motion versus whatever we discussed earlier, right? That a simple case where you had just a body rotating in a circle, right? When the body was rotating in a circle, it was just that the v was tangential and the magnitude was going to be constant. But here that's not the case because there is a retarding force of mg sine theta which is acting against the velocity, right? So this is the major, I mean, this is the overall of understanding of the forces that are acting on this particular small m. So okay, so that was about the velocity. The velocity is changing in magnitude as well as in the direction. So the next question is, will the momentum remain conserved or will the momentum value not change? So no, right? The momentum is also going to change because your velocity is changing, your direction is changing. Even in the case when it was a simplified version where we had the body moving in a circular path, there also the momentum was changing because the magnitude of the velocity was anyway changing. Although the direction of the velocity was changing, therefore the value of p vector, which is the momentum vector, was also changing. But now, in this particular case, there is change of both. I mean, both the direction as well as magnitude. So in this case, definitely the p vector is changing. The only difference between this to the earlier version of simplified case was that in the previous case, the magnitude of the velocity was not changing, and therefore the magnitude of the p vector also was not changing, which means that the magnitude of momentum was not changing. So that's about the momentum. Now let's talk about another important aspect, which is the energy. So now, is energy being conserved here or is it not conserved? If it is conserved, why? And if not, why? So we will discuss about the topic called as conservation of energy and try to understand that whether this conservation of energy holds good here or not. And if, but before that, the conservation of energy, we should understand that whether even the conservation of energy can be applied here or not, right? So the topic is conservation of energy. Now, when does the energy get conserved? As the word says, the conservation of energy means that the energy is not going to change. The body is not being added with any external work or any kind of work is not taken out, right? So there is no input or output of the energy from the existing system. Therefore, the energy is getting conserved. Now, what is the meaning of this? The meaning of this is that if there is a body A, and then suppose there is another, not the body A, the point A, sorry, and there is another point B. So at this point, if there is a body placed, its energy is going to be same. It's not changing. And if there is another body placed at point B, its energy is also going to be same. So then we can say that for this particular body, the energy is conserved. There is no change of energy. So, okay, so now having understood that, the next point is, when does the energy conservation happens? So since we are talking about mechanical systems right now, right? We are not talking about electromagnetic electromagnetism, or we are not talking about wave theories and all that, right? We are just talking about mechanical energy, or we are in the mechanics, right? That the physics branch is called mechanics, and here the work done is solely dependent upon the force, right? The force is the player who is driving this work done. And how does it drive? It is simply F into D, F dot D, right? FD dot product. So force multiplied by the displacement, that is what gives you work done. So it is very important now to understand that what is the nature of the force if suppose the energy conservation is going to happen, right? So here the main thing is that the force which is acting on the body, right, should be conservative. Force should be conservative. Force should be conservative. Okay, to make the body preserve its energy. So force has to be conservative. Now, what is the meaning of the force has to be conservative? So if if the force applied is conservative, we understand that the body under the influence of a conservative force um, is not going to change its energy if it comes back to the original position. Obviously, it can change energy if it is going from, let's say, A to B or B to C. But the point is that when it returns back to A, the net energy is not going to change. Therefore, at the point A, the energy is conserved. Okay. So we will try to understand now that what is the meaning of this conservative force. Now, to understand conservative force, we need some higher mathematics, vector algebra, right, and all that. So I'm not going to go in those details right now. I will just explain in a very simple way what is applicable, and maybe subsequent classes, I can explain in more detail about how you can find out whether the force is conservative or not, what is the meaning of curl of a force vector, and why the curl of a force vector should be zero in order to make it conservative. But all that things is beyond the scope of right now's discussion. So we will skip that part. But yes, we will try to understand like which force we can call as a conservative force. So a conservative force is that force where, so let's say suppose the body is there at point A and it has to go to point B. So if it has to go through this, it can go in any path, right? From A to B. It is, let's say it's going in this path. Another way, let's say it's going in this path, right? If the if the work done, right? If the work done. So obviously when the body is moving along this path, let's say A to B, if it's going along this bottom path, it will do some work, right? Because it is getting displaced and also it is having a force. So some force is acting and it is getting displaced. So it will do some work. So for moving from point A to point B, the amount of work being done is same along this path, or you take any other path for that matter. So these are just two paths I have taken. You can take any other path. So the work done would be same. And what will be that work done? The work done will be solely equal to the energy of this body at point B minus energy of the body at point A. So what does this expression mean? It means that the work done is first of all same whether you go through any of the path. And second thing is that it is solely dependent upon the initial and the final position. So it is independent of the path, independent of the path, independent of the path. The work done is independent of the path. And the another important factor of this force is that this force is the energy. So the force is such that it produces a work done which is independent of the path. And the second point is that the work done only depends on only depends on initial and final condition, initial and final position. It only depends on initial and final position. If this is the situation, then in that case, I can very well say that this force must be conservative. Now, there are multiple scenarios. Like you can take simple case of a gravitational force, right? Let's take the example of a gravitational force, G, right? mg. Okay, so this is a gravitational force, right, acting on a body of mass m. So now this force, whether it's conservative or not, will depend on if suppose the body is moving from, let's say, position A to position B, the change in the energy is solely dependent upon the energy at this level and the energy at the another level B. If the work done is only dependent on that, then we can say that then the force, this gravitational force becomes a conservative force. So we already know, right, that the energy over here can be given as mgh, right? So depending on the height, whatever the height of A, that will be mgh. At this point also it is mg. Suppose it is h1 over here, it will be h2 over here, mgh2. So there will be height of A and B. And the energy, the potential energy to be precise, the potential energy is only dependent upon mg, upon only the height of the body. Now whether you come to this with this path or whether you come along this path, it doesn't matter. The point is, if you are coming from this point to this point, your energy change, the potential energy change is mgh1, mgh2 minus mgh1, final minus initial. So therefore, this gravitational force is a conservative force. Let's take another example to understand this. So now, one more thing before we go ahead. We were talking about point A and we were talking about point B, right? So I said that you take any path and you go from point A to B, the work done would be same, right? The work done would be same, and that is if the forces are conservative. Now, because it is independent of the path, basically. So the meaning of this is, if suppose I go from point A to point B and along this path, and then let's say I'm trying to return back to A, right? I'm trying to go this way, and then I'm also trying to return back, right? So then what happens? Since in going the energy being spent is, let's say, delta W. in while returning back, the magnitude is also going the magnitude is going to remain the same, right? But its value will become minus delta W because this time you are coming back, right? So it will be minus delta W. So if you add the total energy, which is the total energy change that happens, it will be delta W minus delta W. So back at the point A, going to B and coming back again at point A. What is the total energy that is spent? It is delta W minus delta W, which will make it zero. So that means there is no change of the energy at point A. And therefore, whatever the energy that we define for this point will remain same, right? And this energy is what we call as the potential energy. Therefore, we got a chance to define an energy because we now know that each of such points, right, each of these points can be attributed a given energy value, right? And I have the scope of defining a energy level right now. So potential energy is, we have defined it like a level of energy that exists at point A because we know that it's not going to change. The forces that are acting are all conservative. So the point is that whenever there is a conservative force field, right? So conservative force field means suppose there is a gravitational field, right? There is a gravitational field. This is G field, okay? And suppose there is a point A, I can attribute an energy level to it. There is a point B, I can attribute an energy level to it. Same way, a point C, I can attribute energy level to it. And that energy level is not going to change, right? Based on the fact that we just discussed, right? That when we are going from A to anywhere and returning back to A, the net amount of energy spent out is zero. So there is no change of energy at A. And therefore, if I define an energy level for A, that is, we know that the body is going to maintain that energy level till the point it is at point A. The moment it moves same way to any other point B, the energy level there will be constant. And that is why we are able to define something known as potential energy if the force field is conservative. Okay. So obviously all these things can be understood through vector algebra in a very, very simplified manner, but I don't want to go in the details of that. Obviously, it will require more mathematical um, uh, calculations, etc. And also we'll need to understand some more formulations like curl of a vector and all that. So we'll not go into those details right now, but we are trying to understand what is the physical significance of this conservative force. So conservative force is that if suppose from one point I'm going to the other point, there is some amount of work I'm doing. But if the same amount of, let's say I'm while going from point A to B, I lost some amount of energy. Okay, there is some loss of energy. But if I'm able to recover back that energy when I return back to point A, then at point A, the net energy change would be zero. So whatever I'm losing, I'm able to restore back. Or if I have gained some energy in the path, while returning back, I will lose that energy. So there is always a restoring of the energy happening. So while I am returning back, and if that kind of thing is happening, that means the force field must be conservative. Now let's take an example of friction, right? So friction force is not conservative force. Achha, before that, since I just told about that the potential energy can be defined for such a field, right? And it will depend upon the position. It will depend upon the position. So the potential energy, let's represent it by U, of at any particular position will be a function of R, R, H, or anything like that you can say. Now, this means that it is going to be dependent on the position, right? If you are looking at R from, let's say, Earth's surface, we call it H. Obviously, we know that potential energy is a function of H, right? If it is a point over here, and if you take out readily any other point over here, then that is R, right? The distance between these 2 points is R. So the potential will be dependent upon R. So here the potential is dependent upon whatever the radius R1 is here. Suppose it is here at this point we are talking, it will be dependent upon this R2. So this will be also one significant factor that you will see, that the potential energy is turning out to be a function of R. For such, and if that is happening, then the force field in which this thing is happening is going to be a conservative force field. So now let's try to understand about the frictional force, whether that force is a conservative force or not. So let's say if I'm going to travel from point A to another point B, right? So you know that if this frictional force, right, it will always act in the backward direction, trying to retard the motion, right? If the velocity is in this direction, it will try to retard that velocity. So it is going to uh, it will act in the opposite direction, and it will manifest itself into what? It will manifest itself into some kind of loss, whether it will become, the surface might become heated up, the energy might be lost as sound energy, or maybe like a heat energy, or different forms of energy, right? Mostly it is heat energy that is getting lost here. So while it moves from A to B, the energy is going to be lost, right? But I don't have any issues with that. From A to B, my energy is lost with whatever the force, this friction force F that we are talking about. The body is having that frictional force F, and while it is going from A to B, the work done is, the energy is basically lost, correct? But the what I am interested is that when I return back to point A, right, back to point A, I should have restored back that energy. I should have gained back that energy, right? If this is happening, then I can say that the friction force is a conservative force. But whether this will happen, now just check. Now, if suppose the body comes to this point and again starts moving back, right? Again starts moving back. Now, what is going to happen? Do you think that this energy is going to, we will gain the energy? No, because now the friction force will start acting in the opposite direction, right? And again the effect will be same. Again it is going to produce more heat, right? It will lead to, instead of gain, it is going to again lose heat, lose energy in the form of heat. Let's say in the form of heat. So it's again going to reduce energy. So that means while I returned back from A to A again, the total energy or whatever was in the beginning will now not remain same, because here also there has been a loss, and while returning back also there has been a loss. So therefore there is a net energy loss which has happened. So therefore, this field is a non-conservative field. The friction field is not a non is not a conservative field. So ideally, there are multiple. We can do the calculations, but for and try to understand for various fields. And as I said, that vector algebra might be required in order to understand whether the field is conservative or not. But for time being, we can understand that gravitational field is a conservative field. So I'm writing all the conservative fields, okay? Which are the fields, force fields that are conservative. So gravitation is one of them. Second one is your electric field. Electric field, all these fields, if you look at it, if you look at their U, which means the potential energy, everywhere you will see that it is a function of R. The potential energy for all this, for a gravitational field, potential energy is inversely proportional to R. So it means it's a function of R. Electric field, same way, it is inversely proportional. Same way, it is like it is inversely proportional to R. So it's a function of R, as I was telling. And that is also giving an idea that all such fields are conservative. So the point is that if the forces are acting on the body which are conservative, the energy is going to conserve. The energy is going to be conserved. This is one thing. Now another thing is that if suppose the body is moving in this direction, and at all the time, remember all the time, the force is acting in the direction in 90 degree to the direction. So where, if suppose the particle is here, the force is acting here. If suppose the particle is, let's say here, if it was, let's say, swinging, and the particle is here, the velocity is in this direction, still the force is acting in this direction. Now this force also cannot do any kind of work, be it conservative or be it not non-conservative, right? Be it conservative or non-conservative, this kind of force, which is always acting perpendicular to the direction of the motion, is also not going to do any work, because it is FD cos theta, right? F dot D product. So which is FD cos theta. In this case, theta is 90 degree, right? So therefore, cos theta will become 0 and there will be no work done. So in such scenarios also, where the force, whether it's a conservative force or non-conservative force, in both the scenarios, if the force itself is acting always in the direction perpendicular to the motion, then in that case, there will be no change in the work. There will be no work done. And if there is no work done on the system, its initial energy will remain as the final energy, because you are not adding or taking out any form of energy in the form of work, right? So therefore, so this is also a scenario. Rest all other scenarios, if suppose if the force is, if the non-conservative force is acting along the direction, or its component is acting along the direction, the energy is not going to remain conserved. As simple as that. If it's a conservative force, right? If it's a conservative force, then its energy is going to, it will maintain a energy level, and the energy is going to be conserved. At a particular point, the energy is going to be conserved. That is important. At a particular point means when it returns back to a particular point, the energy is going to be conserved, and the energy is going to remain same, and the total energy is going to be conserved. So when I say conserved, it means that if suppose the energy at a particular point is let's say dependent on R, so obviously this potential energy is changing, right, as I move away, or depending on the radius it changes, but the total energy of the system will remain same. And that is where you see in the mechanical energy there comes another factor, which is kinetic energy. So the as the potential energy goes up, the kinetic energy will reduce. If the potential energy reduces, the kinetic energy will go up, right, so that the total sum of the energy remains same. So mechanical energy is going to remain same, and there can be only two components to it, right? When if we are talking about mechanical energy where force is playing the role of deciding how much amount of work is to be added or subtracted, then mechanical energy is the combination of potential energy, which is defined because of the fact that at any level I can have a consistent amount of energy that I can define, right? Because when I return back to after doing all the things to that particular point, my energy is not changing. Therefore, it makes sense that at a given point I define something known as the potential energy. And then obviously there will be another form of energy because of the motion, which is called as kinetic energy. Now this energy, um, obviously as the radius changes, as the height changes, as the position changes, the U energy, which is the potential energy, is going to change, and accordingly the kinetic energy is going to change, right? But the sum total of these two energy will remain same for the entire system. So in the entire system, if the forces are conservative, the mechanical energy of the whole system is also going to remain conserved. So I hope this is clear. Now let's look at our original question and see that whether conservation of energy can be applied or not. Now looking back to our original case, if you see here, there is a first of all there is a there are two external forces that are acting. One is the gravitational force, and the second one is the tension force, right? So gravitational force, we understood it's a conservative force. Therefore, it will make the system conserve the energy, right? The entire energy of the system will be the entire mechanical energy of the system will be getting conserved. And also, I can define a potential energy at any given radius, right, or at any given height. And the second energy which is coming, the second force that is coming into play is the tension. Now, is tension a non-conservative force or a conservative force? So tension is a non-conservative force, right? It may produce a loss of the energy, or it might produce a gain of the energy depending on how it is acting on the body. But here, as I explained you that in this case, it is always acting in this VCM case, in the vertical circular motion case. This is always acting perpendicular to the motion of the body. This is always acting perpendicular. So that means whether it is conservative or whether it is non-conservative, we know it is non-conservative, but I'm just saying that if whether it's conservative or non-conservative, it is not going to do any work, right? So it's not going to add any energy or reduce any energy. So this T is not going to play any role in defining the energy of the body, because it's not going to do any work, right? So the only component that plays is the G, which is the which we know is a conservative force. So the entire energy of this system, I mean the mechanical energy, which includes potential energy and kinetic energy, is going to be conserved in this scenario. So now, and since it can be conserved, I can say that at any point, let's say at this point, if the velocity is v, the kinetic energy can be given as half mv square plus mgh, right? H can be defined with respect to any location. You can take point 1 as the location, or you can take origin as the location. Depending on your point of reference selection, you can define the value of H. This is going to be constant. So this is the sum total of the energy. This part is mechanical energy. Since there is a conservative field force which is playing the role, and the other part, which is tension, is not doing any work. Therefore, the entire energy, mechanical energy of the system, is going to remain constant. Okay, and the potential energy also, we are seeing that since it's a gravitational field, which is a conservative force, I can define a potential energy which is mgh, which is depending on its position, right? So mgh is the potential energy which is defined for this body. So now I hope this is clear, and when we study the chapter in more detail, then we will further clear each and every concept about these things, and maybe we can go a little deeper and discuss about slide vector algebra to gain some confidence in deciding whether a field is conservative or not. But for time being, now let's take up a question here. The question is, the body, which is a point mass is doing VCM. VCM means vertical circular motion, right? Um, and it in a circle of radius r, right? It is tied to a string. So it is tied to a string, right? And it is moving in a circle of radius r, which means the length of the string itself is r, and it is doing a vertical circular motion. So we have to find, number one, critical speed or yeah, critical speed of the mass of this particular mass. And second thing, we need to find the speed, which means magnitude of the velocity. So magnitude speed at lowermost point, lowermost point or the lowest point. And the third one is your you need to find out what is the tension maximum. What is the maximum tension occurring in this string? So try to solve this problem. It's all based on the concepts that we talked about. And just to explain critical speed is the minimum speed at which the body is just going to do the VCM, right? It will not, the string is not going to get slacked and fall off. It will just complete the circular motion. So what does that mean? That at the highest point, the tension becomes minimum, right? So we'll see that when we are solving that. So, but the tension becomes zero, and there, whatever the velocity that is coming, whatever the speed that is coming, that is your critical speed. If you go below that speed, it means that even before reaching the topmost point, just before reaching the topmost point, the string is going to get slack, and the body will not be able to complete the entire circular motion. It will just fall off. Okay, so that is the critical speed. That's what the critical speed means. So yeah, try to solve this problem, and then uh, look at the solution. Okay, so now let's try to understand this problem. And so there is a body which is there, which is moving in a circle. So this body has, let's say, at any particular point, I can find out that if this is the tension, this is the mg acting. I know if this angle is theta, then this will be mg cos theta, and this direction will be mg sine theta, right? And let's say it is having a velocity of v. So what is the equation? The equation says that along the radial line, I can put T minus mg cos theta as the resultant force inward, and that will be equal to your mv square by r. Now imagine at the highest point, theta is equal to pi, right? When theta becomes pi, that means the body has reached at the topmost point. Now what happens there? This will become T plus mg is equal to mv square by r. mv square by r. Now, this is the point where your velocity is going to be minimum, because we already discussed that the velocity is reducing and reducing as it is going up, right? So because of this retardation that is happening all the time, mg sine theta, the body, and as it is picking up height, it's the value of the velocity is decreasing. So at the maximum point, the velocity at this point, let's say a, the value will be minimum. The value of the velocity will be minimum. So this is one expression which is coming. Now, if suppose at this point I need critical speed, so that means the minimum speed that the body can tolerate before it becomes actually the body falls off. So in that case, what should happen is that at least till the point the body is here, this string should have some tension, right? Should have at least some tension. If if the tension itself has gone, let's say here itself, if the tension goes away here itself, at this point itself, then the body will fall off, right? Body will fall off from here. It won't reach at this point. So therefore, the tension must become, the tension should be in the limiting case, the tension is zero. Tension is zero at highest point. That is what we want. And why we want at the highest point? Because if it remains here at the highest point, just after this, it will again gain the tension, right? It will again gain the tension, and then it will keep on rotating with the tension in the string. The string will not never become taut. So at this particular point only, since it is having the minimum velocity, the tension whatever is existing plus mg will give you mv mean square by r. Now, if you have given sufficient amount of tension, well, it is okay. I mean, tension will still exist at the highest point. But we are talking about the case when it is it is having critical speed, which means even the tension has gone. So now if you go below this speed, the body is not going to complete the circular motion. It is going to fall off, right? So that's where I'm putting t is equal to 0 to gain the to find the critical minimum speed that is possible at A. So here I will put t is equal to 0. So now in this case, you can see that mg will become equal to m v. Now v minimum is the v critical, because even with v minimum I was having some tension. If I've given sufficient amount of tension, some amount of tension will remain at the top. But now I'm cancelling out that also. I'm thinking that that tension is also not there in the limiting case. If suppose that tension is also not there, the body will just go and just pass out, and therefore it will just complete the circle. Okay, so mvc square by r. Therefore, now you get that vc will become equal to root under gr. So this is one case where your velocity at the top should be minimum root under gr, such that at least even with a zero tension on the top, the body is the string is not getting slack, and the body is not falling off the trajectory. So it is just completing the trajectory. So now this is your VC. Now another thing as was to calculate the velocity at the bottom at this point. Here we have to calculate the velocity. Now I can calculate this velocity using all the calculus, everything, right? That means if I go through this method of calculation, I will have to find out everywhere what is the force body diagram, right? And based on that, the components of velocity, and then what is the force acting in x direction, what is the force acting in y direction. Then I will check like how much acceleration is happening in x, how much acceleration is happening in y, and then following this path, I will have to see that the body is coming from, let's say, plus h to minus h from the A point to this point B. And in that, what is the vertical change in velocity that is happening? What is the horizontal change in velocity that is happening? And then calculate the final V over here. So obviously, we can do that if we know calculus and all. And obviously, even if we know calculus, this process is going to be time taking, right? We will need some time to do that. But it's not that we cannot do. We can very well do. So that is where, in order to simplify this process, we can use the energy conservation, because we know that in this system, the energy is the energy is conserved, right? The energy is conserved. So we because of the fact that G is acting downward and tension is not playing any role in the in gaining or in doing any work on this system. So the energy of the entire system is constant, the mechanical energy. So the potential energy at B plus the kinetic energy at B must be equal to potential energy at A plus kinetic energy or at A, and that will help me to get the value of the velocity at point B in just one equation. So it makes my life easy. That's why this conservation of energy is important. So now, since we can define the reference of to decide h, right? I can, let's call it, I have defined the reference as, let's say, this point, or let's define it as b, right? This is my b, this is my a point, right? Let my reference be here. Okay, this is my reference height, and reference height I call it as 0, so h is 0 over here, right? Here the h will be what? Here the h will be equal to 2 times of r, 2 times of r. Now I can apply the energy conservation. So at point A, I can write half mv square plus mgh. This will be nothing but half m. V is vc square, because this is the case where we are having vc velocity at A. What is the maximum velocity? What is the velocity at B is what we are trying to find out. So here it will become gr, mgr plus mg, and h is going to become 2r. So if you do the calculation, this will come to mgr and 2.5, right? So it is 5 by 2 mgr. This is what we get, right? 5 by 2 mgr. Now at point B, if I look at point B, if I look at point B, the mechanical energy can be given as half m velocity at point B given the critical speed at A. Given the critical speed at A point, right? The velocity of B given the critical speed at A. Square of this plus mgh component is going to become 0. Mgh will vanish because your h is 0, right? It will vanish out. So this is what is your energy which is happening at the bottom. And now since the energy at A and the total energy, mechanical energy at A and B are conserved, that means the energy must be same. Therefore, I can equate it to these two. I can equate, right? So that means your half m v vb when it is critical at A square must be equal to 5 by 2 mgr. Now doing slight calculations, you can find out that vb for critical at A square is given as 5 gr root over. So this is, now you can take out this square, has I have taken the root over on the other side. So therefore this is equal to your root under 5 gr. This is the velocity at the point B. When the velocity critical at the point A is root gr, we get root under 5 gr at the bottom. So that is the second part of the question. Now the third part of the question was saying that what is the maximum tension? Now tension obviously is, it is given by this, right? It's given by this formula, T minus mg cos theta is equal to mv square by r. Now when is the tension minimum? What is the maximum tension? The maximum tension obviously will be when theta is 0, because at theta is equal to 0, what is going to happen is that m cos theta will become 1, so it will be T minus mg is equal to mv square by r. T will become mv square by r plus mg. So it is addition of mv square by r plus mg, and that's the maximum tension that can happen. So we'll use that, and that is happening at the bottom because theta is equal to 0. So at theta is equal to 0, your tension will be equal to mg plus mv square by r, right? And this will, the velocity here will be b, right? Because b when c is critical, when speed at c is critical. So with this calculation, you can find out the maximum tension, which is mg plus m into 5 gr by r. R cancels, you get 5 mg plus mg, which comes out to 6 mg. So 6 mg is the total tension in the string that happens. So I hope this clears everything, and it was a good problem. We went in quite a detail about in this problem and tried to understand each and every concept. Um, we will solve more problems like this. So please follow us on our channel, and for more videos like this, you can reach out, as I said, at any point in time. So keep studying, keep doing the good work. Thank you. We'll meet again.